Ladies and gentlemen, it is my honor and privilege to represent our team in this 2021 Future Tech event. The title of our project is Autonomous Cruising Unmanned Underwater Vehicle. I'm Chao-Ching Wang. The success and credit of this project shall go to every member from different universities in the team, whose names are given on the screen. Besides, I would like to express our biggest appreciation to many of our friends, including Tori of NARLab and the Zhongxin Shipbuilding Group. Let me cut to the point to highlight what we managed to develop in this project. The bottom line is we'd like to introduce AI into the unmanned underwater vehicle so that it can cruise in the ocean and execute certain operations efficiently. After AUV is equipped with AI, AUV not only is able to do the object recognition, it is expected to execute many more complicated functions like following special object and swimming away from any dangerous object. Because the power capacity of any AUV is limited, new AI algorithm and architecture with low power dissipation are very much demanded. Everyone knows that AI training needs massive amount of data. However, the pictures of these underwater objects are not easily obtained for AI training. Therefore, we need a special approach to enlarge the training data set, which is 3D modeling in our project. The water becomes totally different at the sea level because big water pressure, no air, no GPS, no radio frequency, and maybe no sunlight. Two major ways for humans to explore the unknown chart under the sea level are remote sensing and unmanned platform. For example, we take advantage of acoustic waves like whales and dolphins. It is a sonar, basically, to check what is going on under the sea, in the deep sea. So we start from a single beam in the short range and use a multi-beam to check wider range and deeper range. In order to look closely to those interesting creatures or the sea floor, many instruments are already on the market, like those in the right-hand side. Please be advised that most of these equipments are no man inside because it's really dangerous for people to stay deep in the ocean. All the unmanned underwater vehicles are mainly divided into two categories: ROV, which has a cable connected to a mothership, and AUV, which has no cable at all. That is, AUV is battery powered. As shown in this table, ROV is obviously limited by the length of the cable, no matter it is self-powered or not. On the other hand, AUV can cruise at will, but it is limited by the power bank that it has. We call this problem of the AUV power wall. So in short, we conclude that we need to overcome two major problems before the realization of AI on AUVs. That is a power problem and training set shortage, data shortage. For the power problem, we need a better, more sophisticated BMS to take care of the precious battery power. What even important is that we need a faster charger on the mothership to help AUV fastly repower. On the other hand, we need other equipment with us. For example, both the thrusters and AUV and AI computation are very power hungry. Without a BMS or faster chargers, AUVs are likely to cruise at will in a large range. The other problem is the training data. For example, we need over 10,000 pictures to have recognition accuracy as high as 95%. But it is almost impossible. Even now, we have very strong, powerful web search tool. This kind of data collection needs paramount human efforts. So to make our dream come true, we adopt a divide and conquer approach to make it happen. Our AI AUV is firstly divided into two parts: the hardware platform and AI on chip, as shown in this table. Then, the upper part is realization of the AI AUV hardware, including the positioning system, navigation system, lighting system, and a sensor hub and array and hub. The lower part and the means to carry out our AI algorithm on silicon to reduce the power consumption. Therefore, we need a lot of things like a new algorithm, FPGA prototyping, and server setup. After all these parts are respectively assembled, we then integrate them together and run it. Okay, this is a very simple example to show how to use AI underwater. Basically speaking, we can roughly classify all the underwater objects into 3 types. Type 1, those things we don't care, like Nemo and other cute creatures. Type 2, okay, those things we like to follow or we are interested, like a diver, we like to follow. Type 3, those things which we like to stay away so that AUV will not run into it, or like a coral or a rock. Okay, and we have developed many new technologies which will be used in the future. The first one is called 3D modeling of the data. Okay, for example, the idea is generate the pictures with multiple viewpoints and change the backgrounds. In this way, we have the following advantage. We don't need to spend too much time and effort to do the object classification. And this modeling approach can be programmed so that a big data set can be generated. And there are 2 examples given here, clownfish Nemo and the diver. Compared with the state of art, our 3D modeling approach can easily generate the number of samples over 1,000 times, which is far better than the 6 times in prior works. The key point here is a change of the viewpoint. Besides, it is confirmed that our 3D modeling can be used to recognize multiple objects in the same frame, no problem at all. This slide shows a benchmark comparison. The left-hand side tells the difference between the traditional 2D modeling and our 3D modeling. We successfully increased the accuracy by 14%. The right-hand side shows a comparison with 2 well-known data banks, ImageNet and the Fish4K. Our methods wins 3 of the 5 KPIs and still is the second best of the other 2 KPIs. For the smooth control of AUVs, we developed hardware in the loop simulation platform and the mission control system, as shown in the left. Then, before system integration, motion experiments of the AUV were conducted in 2 water pools in our school, as demonstrated in the right video. It is a must for AUV to know where it is in the dark and no GPS environment. We then developed the approach, use a common filter to merge measurements from DVL and USBL positioning system. The precisioning error of our approach is only 0.2% of the travel distance, which is smaller than 3.4% by traditional methods, as shown in the left. Our AUV also assigned 1 mission to carry out remote sensing to tell what the seabed material is. So we equipped a light sonar system and to transmit and receive reflected acoustic signal, which are filtered and beamformed and passed to the AI processing, so that to analyze the surfacial sedimental properties. And the most important AI algorithm developed in this project is given here. Because of the limited power on AIUV, our team proposed a new architecture, okay, for the convolutional neural networks. Basically, it is featured with the RFE model, okay, consisting of expanded layer, a squeeze there, and a max pooling there. Not only AI that we develop is able to recognize efficiently, we also can detect, it has a capability to dehaze and defog the images and enhance the color contrast. Our AUV can also be equipped with underwater SLAM and a side-scan sonar to detect objects in the bottom of the ocean. As shown in these figures, the extended common filter and the SLAM are used to estimate the positioning of special objects in the water and the state of the landmark. Lighting is required in any underwater operation. For AUV to recognize object correctly, the color of the target is critical. However, the lights with different wavelengths are fading differently. For example, the red light is the worst one. That is, we need an intelligent light color compensation system to compensate the mixed white light of light energy with the distance between the light source and the target, so that we can have a very good recognition. In this video, we are going to show you that AIUV combined with the development of 3 sub-technology, including AI diver detection, diver following method, and the payload sensors. No matter where the target diver goes, AIUV will be right behind him. This is proof of real time in water testing. Another feature is that AIUV can detect dangerous objects and swim away, as shown in these video clips. By integration of image processing and the forward altimeter signals, AIUV is able to detect the dangerous object in the water and steer away. The right-hand side shows its trajectory looking from the top. Real open water testing is automated testing for AIUV. We took our AIUV to Tainan Anping Harbor. Thanks to the strong support of Tory in early 2021. The AIUV cruises freely in water and then comes back home. This demo proves that the technology about navigation, control system, and the user interface for unmanned water vehicle is good. It is not easy to make comparison with AIUV developed in other countries. However, we managed to dig out some public information of AIUV developed in Japan, USA, and China. It seems that our AIUV looks just fine, except that it is a little bit too big. The reason is our AIUV is still an open frame prototype. It can be polished much better in the future. This slide shows what we have achieved in this AIUV project. In short, our team integrates a variety of cross-domain knowledges to equip the underwater AIUVs with AI. Not only object recognition, precision is maintained as good as that in the land. The self-righting, object tracking, tracing, barrier avoidance, and the function in the water are fully demonstrated. Thank you for your listening. The last 2 videos show our AI capability realized on FPGA, and I am the diver in this video to test this AI on my own. Thank you again.